3 of lecture 10. So in the previous two parts, we talked about a general Bayesian network, and we actually never talk about classification problem. So we are treating all of them as features. So in the example, I kind of talk about if one of them is the label, what should we do? But here, there is a special, very simple Bayesian network structure that is specifically used if there's one clear label and all of the other variables are features. And it's called the naive Bayes classifier. And that a naive Bayes classifier assumes that these features are independent, but they are both all of them are dependent on the label y. So I think I drew this before. Let's draw it again. So we have the y, and all of these x, they are causing y, x1, x2, x3, x4, and x5. So this is the network structure that we're going to assume, and then we're going to train these conditional probability table, and then basically we can compute these probabilities, the probability of y is y, given all of these x take on some particular value, and we just figure out which y maximizes this probability, and we use that as our prediction. So the idea is actually very simple. The training is even simpler. We have all of these conditional probabilities, and then we go over all the possible y values and figure out which one is largest. That's basically all you do. So, and also they are independent, so we can take the product of these x given y's, and basically we're going to use Bayes' rule to do that. You are actually doing this in P3. So during the lecture, I'll actually talk more about this, but here I will just leave it as this expression. And remember, you need to compute this by doing y and x divided by x. And if you expand this the same way as I did as the product of multiple things, you can see that this is actually something called Bayes' rule, and it's cool. Okay, but let's talk about more theory. So the implicit assumption actually we're using, and we're calling this the maximum likelihood, and it's basically what we did, is counting the number of times x, y occur at the same time and divided by the number of times y is occurring. The assumption is that these distributions follow a multinomial distribution. So if you have not taken statistics courses, you may not know what distribution is, but I'm not going to talk about this in a lot of detail as well, because it's not that important. So all you need to know is we are doing this as the maximum likelihood estimation. And there are some kind of very formal statistical theory behind this, but again, I'm not going to talk about this in detail. And you may want to ask, like a long time ago, what happens if x is continuous variable? It's not like x is 0, 1, or 2 or something, because this assumes they are 0, 1, 2, then we can count it. Otherwise, all of the counts should be 0. I mean, most of them. There is actually a way to replace this multinomial distribution by something called a normal distribution or a Gaussian distribution. And the naive Bayes, with x variables being continuous, and we assume that they follow some kind of normal or Gaussian distribution, is called Gaussian naive Bayes. And the assumption is this probability, the probability that our x, which is a continuous variable, fall in a small interval from x to x plus some very small number epsilon, very close to 0, probably has this expression. And this thing is usually called PDF, probability density function. So again, if you are not familiar with this from some statistics course, is not that important. So we're just going to assume x given y follows some kind of distribution, and there are parameters in the distribution that we need to figure out. These are like the weights, and we need to figure them out. It turns out we don't need gradient descent for this. There is actually closed form formula, like for just the same way we had for like the maximum likelihood with just counting the number of times something occurs. There are like explicit formula. You can differentiate this, set it equal to 0, and directly solve it. Of course, we're not going to do it here. And the solution is very simple. It just says we take the x value. So for the mu parameter, which represents the mean of the Gaussian distribution, we are just taking the average value of the x for the x with label y equal to that particular y. And next, we're just going to take the variance to estimate this variance parameter of the Gaussian distribution. Here is sigma squared, and that expression here is basically the expression for the variance of basically a lot of points, and there is a sample variance thing as well, but this, by definition, this population variance is the maximum likelihood estimator, but many people also use the sample variance, which the only difference is there is a -1 here. So again, we will not go into a lot of detail with this. If you are familiar with these, you already know that these things are maximum likelihood estimator. If you don't, you can just take them as given, some formula from just maximizing the probability of getting these data points. Okay, so let me actually give you an example. I remember I did this before, but let me repeat it. So we have some, say, cats and dogs, and what we're estimating is we're estimating, given the label, what is kind of the distribution of the x. And in particular, there are two x's, x1 and x2. So we're kind of estimating the joint distribution. So the Gaussian assumption is basically we have a mean in both directions. This is our mu1, this is mu2, and there's a kind of a variance. What I'm saying is not exactly right. So there is a mean if it's the first class or the cat class. This point is mu1 and mu2, and we have some kind of variance in both directions. This is sigma 1, this is sigma 2, and this is sigma 1. And like 90% of the data falls in an ellipse like this, and then we have 99% is in here, and so on. Basically, it follows some kind of distribution that, like in each region of the plane, there is some associated probability with it. So we are basically estimating these 4 parameters that specifies that distribution. And for the same reason, we can figure out mu1, mu2 for the second group, given y value is, say, dog. And then we still figure out sigma 1 and sigma 2. And then still, most of the data is in this region like that. And one thing that's very useful is, given this distribution, we can actually generate new sample points. So again, going back to why these are called generative models, we can use this distribution to generate new points, and the new point is very likely to be kind of close to the training points. And that's basically what we're doing here. Okay, so the last thing, we can have a tree connecting the axis and all of these x connect to y. And this algorithm is called the tree augmented network algorithm, or the TAN algorithm. So the only difference is we are going to compute the information gain as the conditional information gain on y. I remember we didn't actually have the formula for that. So I think I'll post a link to this on my website so that you know the formula, but most likely you are not going to compute this anyways. But the idea here is we have y as a special node, and everything is causing y, x1, x2, x3, and x4. And we start with the kind of all connected x thing, and then we figure out the conditional information gain conditioning on y, and then we figure out some kind of special structure between these. So maybe at the end we have this, and maybe we have something like that. So these x's form a tree, and all of them are connected to y. So remember, this is just a special kind of Bayesian network. So we can do inference the same way. Basically, if we want to get y given x1, x2 until x4, so x3, x4, then we can do the same thing as before for a very general Bayesian network, using the formula that we went through already for the example. So the inference part is actually the same as a standard network, and the training is just we assume the edges behave like this. We first need to figure out the edges between the axes, the features, and then we train all of the conditional probability tables. There are a lot other than the ones that's x given y, because the axes are connected as well. And then the idea is basically the same.